Welcome back to System Software, everybody. Let's give a minute or two for more people to join. In the meantime, I will put up the current syllabus and lecture notes. Okay, let's get started. Just a reminder that on the main page of web courses, there is a list of all of the important links for this course. So you have the syllabus. If you're here, you already know where the Zoom lecture and lab broadcasts are. The video recordings are available in the Zoom tab. If you go to the Zoom in the navigation sidebar and click on Cloud Recordings, you should see all of the recordings from last week's lecture and both labs. Office hours, I saw some people came to the gather.town office hours. And Piazza discussion board, which I think plenty of people have signed up for already, and the GitHub classroom sign-up links. Okay, somebody asked about following along. For today, I'll get into it, but following along, I think we can treat this as a bit of a broadcast, almost like a podcast broadcast. I'll certainly take questions during the talk, but because of it's harder to engage with you the way we could in person, because I can't really see if everybody's following along. But for the first couple of classes, there's going to be very practical classes where you should follow along on your laptop or your computer. Okay, so that's just a quick overview from last time. This is the website for the course that has the syllabus and lecture notes. You can get to it from web courses. And notice that I post the lecture notes for each course or for each lecture, each week's lecture, here under the lectures section. So you can find last time's lecture notes, which is basically the slides in note form, plus some comments, extra comments that I had during the talk. And today we're covering system tools that we'll need for this course. And you'll find the same notes that I'll be going over in class with the slides. Okay, any other questions from last time? Someone said Vagrant takes so long to boot up. Yeah, it depends on your machine. It's basically simulating a piece of hardware in software, so it can be slow. If it's the first time you're running it, then there's a lot of stuff that gets downloaded and installed the first time you create the machine. Okay, yeah, I understand also some people are having trouble with Vagrant. Ask on Piazza. There's some common answers there already. So check out Piazza for some of those common answers. Okay, let's get to today's lecture. So today is going to be a little bit unique. We're going to basically do a lot of stuff on the command line. And I know many people may not be very familiar with using the command line, but one of the reasons that I want to go over this is that, as I talked about last time, I think on the technical side, there's three things that great programmers are good at, and that's the programming language, their programming environment, and some computation theory. And today we're going over that second item, knowing your tools, knowing your programming environment. Without that, programs are just ideas in your head. The programming environment is what lets you take those ideas, those computational ideas, and make real physical machines that execute those ideas automatically. When you use the command line, you also have access to a whole bunch of really powerful and fast tooling, some of which is not easily accessible through graphical interfaces. Graphical interfaces are really, really good for usability and readability and ease of use, which are all great things for programmers. But under the hood of those tools is a lot of the same kind of software that you have a little bit more direct access to when you're using the command line. For some of you who are already familiar with the command line, some of this might be review or it might be boring for you. But I think for most of you, I think there'll be some commands in here you've maybe never seen. If you've never used the command line before, then this will be very new for you. So we're going to cover some basics of the command line. We're going to cover what the file system looks like. We're going to get into a little bit of very basic operating systems, because in order to understand how your program runs, we need to understand how it interfaces and interacts with the operating system and the kernel. And I want to go over this because it's very easy to get a kind of superficial view of the operation of your machine by only using graphical interfaces. For instance, when you get the File Explorer, behind the scenes, there is a file system that provides you this hierarchical file structure. And that kind of structure can be a little tedious to work with, so the graphical interface provides you very usable tools for dealing with that. But on the command line, we have all of the details of the file system exposed to us. So I want to go into a little bit of that. Then I'll show some useful utilities. We'll go over Git. Git is essential for submitting code in this class, but it's also one of the most popular version control tools that if any of you do any kind of industrial programming or even open source or your own projects, you'll probably encounter some sort of version control. And we're going to do it solely on the command line, which will give us all of the nitty-gritty about how what commands these version control tools provide to us. Then we'll look at our classic programming tools that we'll use for this class, GCC and Make for building projects. Now I'm going to go probably pretty fast through some of these tools. There's tons and tons of stuff I want to cover. Rather than being a comprehensive introduction to using the command line, I am hoping that you'll follow along in your Vagrant machine. If you're not using a GNU Linux-based operating system or any Unix-based operating system, then Vagrant is essential for giving you that Unix command line experience. And in this class, I don't expect you to remember everything. A lot of these tools and using them is really about almost muscle memory. It's almost a skill, like playing an instrument. And so the more you just do a little bit of rote practice, the more you'll just remember how to use these tools. Many of them are very, very simple. The Unix philosophy is to have a tool that does something very specific and do it very, very well, and so that you can combine it with other tools to do whatever programming environment or programming task you need. So the first thing is we need to have our Vagrant virtual machine running. So if you haven't set that up yet, then a little refresher is from the folder where you downloaded the Vagrant file, run Vagrant up. And if you haven't set this up already, probably should have sent out an announcement, or actually, yeah, then make sure you run Vagrant up. I've already done that, so it's telling me that it's already up. It might take your machine a second to do. And once that's done, run Vagrant SSH. So I strongly recommend that you follow along and try to type out these commands, or at least watch the recording and follow along. And as I said, this won't be a comprehensive description of how all these tools work. It's more like a follow along exercise to get you started on learning muscle memory for using the command line. Once you do this, like any rote practice, you'll become much more proficient at using these tools. And I guarantee you that you will have more control over your machine, and you'll be able to do much more powerful things more quickly. Yeah, if you still have issues with Vagrant, so there's no late penalty on the Vagrant exercise. The Vagrant exercise is really just to make sure that you actually try to install these tools. So to give people a chance to fire up some of their virtual machines, there were some questions on Piazza about this virtual machine running in the background all the time on your machine. You can always run Vagrant suspend. That will freeze the state. The state of a machine is its processor and its RAM, basically, excluding I/O and peripherals. And if you can save those, then you can stop the machine and restart it and reload that state, and your machine will be in the exact same place you were before you suspended the file. If you're still having issues with Vagrant, I'm assuming that you've already installed it, because it's not due now, but it's due tonight. But if you haven't installed it yet, I recommend just following along in the course or watching it later and following along in the command line. You can also shut down the machine by either using sudo shutdown -h for halt and now. This will allow, I don't run this now, but this will allow you to shut down the machine. So I put a little hash symbol here. That means a comment. So this, just like in Python or the Bash scripting language, that won't get run. But don't run to shut it down. I hope nobody ran that. Or you can use, if you leave the machine, so I left the machine using Control-D, you can also say exit. You can also say Vagrant halt, I think it is. But don't run that either. Okay, let me say the commands that you should run. I probably shouldn't trick you into destroying your virtual machine. Okay, let's let's go through our course here. Okay, so let's start with the command line basics. These notes are really just a reminder of what I want to cover, not so much a comprehensive guide. There are lots and lots of guides. I have links at the end of this lecture for you to read up, and some games that you can try that are very popular among students to learn the shell. But I just really want to kind of conversationally go through and show you really all the commands that I use when I'm doing development or research, and answer any questions that you might have if you're curious about how to do something. Just like in everything in computing, search engines, Google is your friend. There's tons and tons of stuff on Stack Overflow, or maybe it's Super User. Stack Exchange is Super User. There's so much stuff you can do with the command line. I can't remember all of it at once, so often I'll just know what's possible and then Google it and just remind myself of what the command is. Okay, so let's go into the very, very basics of the command line. And as I said, for some of you, this may be familiar. If you've used Windows, some of these have overlap because some of this tooling is decades old and influenced a lot of other system software and operating systems. All right, the very first thing is CD. CD stands for change directory. We'll go over the file system a little bit, but I'm assuming you have some intuitive knowledge of the file system. We're going to change directory to // In the GNU Linux environment, tilde is a special shortcut to your home directory. The home directory is where your files live by default. These Unix systems were originally multi-user systems. So the file system was set up to provide each user their own space on the file system. To see where you are in the file system, type pwd, print working directory. That's where we can see where we currently are. Okay, so there are some questions about Vagrant. If you haven't installed Vagrant yet, I would recommend just waiting. You could also try to follow along on Eustace or any GNU Linux installation you have. It takes a long time to download and install all the software. So somebody asked, can you Vagrant init a different machine? The machine that I provided is just the Ubuntu official Vagrant image. So I mean, if you look in the Vagrant file, it's the same thing. The reason that I provided you a Vagrant file is that there's a bunch of software that I have automatically installed on your machine, but you can open up the Vagrant file and find that stuff yourself. At the bottom of the Vagrant file is all the commands to run to install software. So somebody is asking about setting up Vagrant. So Vagrant up, actually, you have to run it anytime the machine is not, the guest machine is not running yet. So if you restart your machine, or you restart your own native machine, or you shut down Vagrant, then you'll have to run Vagrant up again. It'll never hurt to run Vagrant up, because if the guest machine is already running, it doesn't matter. Okay, so Vagrant issues, let's take them to Lab and Piazza. For those of you who have Vagrant running or have access to a command line, follow along as best you can typing. And if you don't have Vagrant set up yet, then this is going to be recorded, so follow along with the recording. All right, so that's change directory and print working directory. So pwd, print working directory, that's where you currently are in the file system. This text here is the prompt, the command line prompt. This is configurable, but by default, it's your username at whatever the machine name is. This kind of at notation, which we see all the time now in social media and email, I believe comes decades ago from these Unix or these multi-user environments. And so this is really useful for knowing which machine you're on. So am I in my guest OS? Am I on a remote machine? Am I on my host machine? If I exit this virtual machine, you'll see that I'm Paul at laptop. And I've configured my, and this is the current folder that I'm in. Returning back to our virtual machine. The last part of this prompt, so it's the username at the machine, the current directory that I'm in. So my current directory is tilde. And which folder is tilde? Tilde is the shortcut in Unix for our home folder. So pwd, print working directory. These are the first things I always do when I'm in a command line is, okay, what files are here? ls lists the files. There's no files here. What directory am I in? Now, as I've talked about before, if you've set up Vagrant the way I described and download your project on your host machine in the same directory of your Vagrant file, the /Vagrant directory will map your guest OS to your host OS. I can get to that folder using cd, change directory. So now notice that my prompt has updated to show me my current folder is /Vagrant. ls lists files in the folder, ls for list. You can think of, it means list. Whenever I'm on the command line, the first things I always do is, well, okay, what's in my directory? Where am I in my file system? That's the important context you need for the command line. It's very easy to open up this shell and just see this very sparse prompt and say, well, what's going on here? What do I do? It's like a text adventure game where you have no idea what the commands are. That's a very, very old reference for you guys. You may not know what text adventure games are, but another command that I just use there is Control L. So I can't actually display the command, but Control L will clear the screen. That'll give you a fresh screen to look at. Okay, so we looked at change directory and we looked at ls for listing the files. Now, if you type change directory without any arguments to it, then that's going to return you to your home directory always. One useful little trick, if you are changing directories a lot, you can do change directory space hyphen. That will take you to the last directory you were in. Very useful command, something I use all the time. Didn't learn this one until maybe last year or 2 years ago. All right, let's look at files. So one very common command that you can use is the echo command. And this is effectively like print or printf in C. All echo does is just print out the text that you gave it. And we can use this in the command line to create files, create text files. I'll go over a little bit more some of the syntax of what I'm doing here, but just to show you some of the basic commands, here I'm creating a new file called newfile.txt. If I look in my directory, the contents with ls, then I see that I now have this newfile.txt created. If I want to look at the contents of a text file, then I can type cat. I don't actually know what cat stands for, but it's cat. Cat will print out the text of a file. There it is again. Someone is saying maybe it's concatenate. Yeah, you're right. It's concatenate. So I typed man cat, which is not a strange hybrid animal, but it is the command for showing the manual page for an instruction. So this is one super useful thing about the Unix programming environment, is that it's very self-documenting as long as you know the right command. If you're unfamiliar, you need a refresher. I use this all the time because I can't remember the hundreds of options that these commands have.
Is that a thing for Windows command line as well?
I don't know, actually. I don't know. If anyone else knows, you can say in the chat whether there is a similar feature. If there is a man page equivalent for Windows. That I don't know. Yeah, so cat is concatenate. I guess that's the case because I mean, that makes sense because cat can take multiple arguments. So I've got this hello world file here, which has nothing in it. I've got from host, which has some garbage text in it. And I can concatenate both files. And you can see that the contents of both files have been printed out here. That's cat. And another little preview of some of the more powerful features of the command line with this little vertical bar, this pipe symbol. I can pass input and output between files. I'll go over that a little more in a second. But you can see that this is equivalent. I'm printing out hello world. I'm passing that to the cat program, and that cat program is printing it out. It's kind of many ways to do the same thing. Tac, this one I know, this is cat backwards. If I do tac and a file, it'll print it out in reverse. So this is a little harder to see. So let me create a new file here. So here's my new file sequence. I catted it to print it out. And if I do tac, it prints it out in reverse order, line by line, reverse order. One command, another kind of essential command that I use all the time on the command line is less. Less is a text file viewer. Now this can be a little disorienting because once you're in here and you try to just type random keys, you're no longer in your shell anymore. So to get out of this less tool, hit Q for quit. So when I do less, it brings up a new program that displays the text file. So for instance, sequence displays the text file, allows me to navigate the text file. I can hit the arrow keys to go up and down, page up and page down, as long as your terminal is set up properly. There are other shortcuts here. So H will give you help to look at what the shortcuts are. But remember to use Q to get out of less. Less is kind of a funny one. The naming is funny. Why is it called less? There was a utility called more, which prints out. So if I do, so more will page through a long text file and tell you how much is left, but it doesn't allow you to backtrack in the file. So someone created a tool called less and said, well, they call it less because less is more, but it's a more fancy version of less, or a fancy version of more. So it's a pun on less is more. All right, that's just basics. Let's go over a few more common commands, so more basics. So somebody asked, what do we have to do to move around in the text file? So let me create, so don't worry about these commands so much. I'm just gonna use a command to create some I just want to create a larger file so I can show that less utility a little bit more. So here's this long file that has 100 lines in it. If I type less, then you can tell where you are in the file. You can tell that you're in the utility because of this little colon symbol here. If I hit up and down, I'm hitting the up and down arrows, or page up and page down, it'll allow you to move around in the file. You can even hit left and right. So it's very hard to see. You should just try this for yourself on text files, longer text files. But if you hit left and right and up and down, you can navigate through the file. Somebody's saying they're not getting that colon, and if they typed less, so it's not an editor. It doesn't allow you to change anything. I would type Q to make sure that to get out, to make sure you're on the command line. One useful shortcut that I actually didn't put in the slides, but Control C, if you hold down Control and hit C, that will kill some utilities. So less, it doesn't kill. It lets you. All right, let's not get into like Control C or other things like that. There's some more advanced stuff we can do there. But for less, just hit Q. Yeah, it's read only. It's not an editor. I'll talk about editors in a little bit. Okay, so let's look at some more basics. If we want to make a directory, we use the mkdir, which is just short for make directory. Remember, ls views what we have in our folder. And there is my directory, which our shell is helpfully highlighting for us. And remember, if we want to change directory into that, whoops, we can use cd. Now, one thing that I'm going to talk about in a second is it may be one thing that's annoying about the command line is you have to type everything out laboriously. The shell gives you one of the most useful features of the shell, which really makes it possible to use efficiently, is if you type in part of the name of a file, like my, and hit the tab. Yeah, somebody's already predicting it. If you hit tab, it's called tab completion. It'll automatically finish the thing you're typing for you. It's kind of like autocorrect, but decades before autocorrect. And if you've got multiple files with similar names, so for instance, I create a new file with touch. So touch just creates an empty file. So touch.empty file. If I print out these files, there's nothing in them. With tab completion, I can type, if I hit tab, it'll only complete to the common prefix of all of the files in your current directory. If I keep hitting tab, it will show me the files that have the matching common prefix. All those string matching algorithms and string operating algorithms that you may have learned in CS1 or CS2, this is where they're used to good effect, or one of the places where they're used to good effect. And then if I keep typing the file and hit tab, it will complete for me. So this is in the notes, and this actually shows the sequence of tabs that you can hit here. If I just hit tab without anything there, I hit tab twice, it'll show me all of the files in the current directory. And as I start typing and hitting tab, it will narrow down a set of files that are available to complete. And then finally, it'll just complete to a complete word for us. Okay, that's tab completion. So again, print working directory to see where we are. Let's move to our new directory, just to make sure we don't get lost. Print working directory, although it's here in our prompt as well, depending on how your prompt is set up. ls shows that there's no contents here. Let's make a new file with touch. If I type ls, I've got a new file in this directory. If I want to return to the parent directory, I use ... is a special folder name that points to the parent folder. There's another special folder name, which is a single dot, which just points to my current folder. This may seem a little redundant. Why would you ever need to point to your current folder? But sometimes it's helpful to be unambiguously referring to your current folder. For instance, as we'll see later, when you're running programs, we may need to specify that we're running a program in our current directory. Okay, to remove a directory, we use rmdir. And now remove directory has some specific restrictions on it. So if I try to do remove directory, it won't remove a directory that is not empty. So there are some commands that'll force remove directory that are not empty, but I won't show those now because they can be easily abused or misused. So instead, I'm going to go inside my current my directory I want to delete and remove whatever files are in there. So somebody's asking if it's more efficient to do these things in the command line instead of the GUI. It really depends on what you're doing. There are some things in the command line that are easier to do because you can use scripting. On the GUI, for instance, if you've got a folder with hundreds of files and you want to select everything that has a certain prefix, that's something that you can write a little script on the command line to do really, really quickly, much faster than going through and selecting them one by one. And because we're all programmers, there's I won't go into the scripting aspect today, but there's a bunch of, you basically have a full programming language on the command line. And we can write for loops, and we can run commands with for loops and branching and while loops and if statements. We have all that at our fingertips on the command line. And for all of these kind of tedious system admin or file management tasks, we can script it. This goes back to Larry Wall's virtues of a programmer: laziness and impatience. If you have a GUI interface and it takes you 10 minutes to search through or click select files, you can do that in maybe, you can spend your time 2 minutes setting up a little script or Googling the Bash programming language for making a script to do that for you. And then the next time you have to do it, you'll be much faster at doing it. So some things are faster in the GUI interface, some things are faster on the command line. If you're doing lots and lots of large file processing, command line can be very useful because it's automatable. Okay, so I've emptied that directory, and now I'm going to remove that directory using tab completion. So if I make let's see if I'll make that directory again. And I can also create files and refer to files without having to have my working directory be in that directory. I can create files using relative paths. I can say the name of the path / the name of the file that I want to operate on. And similarly, I can remove that file. So I use tab completion to write this really fast. All right, other basic commands. I know, so for some of you, this might be you might have seen this already, but let's say I want to copy or move files. Copy is the CP command. So if I want to copy this long sequence, so let me give you a view of my current directory. So I've got, we got to make a new directory. So here's my new directory. And I want to copy this long sequence file into new direct. Whoops, I just copied it to new. Let me undo that. So I want to copy long sequence. So this is my tab completion fail. There's multiple things named new. So I want to copy long sequence to new dir. And helpfully the command line, the tab completion will put a / at the end of directories for you, making it really, really clear that it's a directory you're copying to and not a file. If I copy to a file, it'll overwrite that file. So that's a little kind of gotcha that you should be aware of. I just accidentally copied it to a file name, different file name, instead of to a directory. And if we look at the contents of that directory, I can use relative paths to ls as well. It'll tell me that, okay, inside of new dir is long sequence.txt. And in my current directory, long sequence is gone. A little preview of how this file system is structured. There's a command that I actually almost never use. I never use this command, but it's useful for showing the command line hierarchy. Tree, oh, I don't have it installed. Oh, that's not good. Sorry about that. I probably should have checked. So if you want to use this yourself, I actually never use this for development. It's really just for illustrating what the command line or what the file system hierarchy looks like. This will show us not only the current directory, but all of the subdirectories and their file contents in this tree structure. So dot is our current directory. It has all these files and directories in it. New dir is one directory, and that directory has a single file in it, long sequence. Don't worry about installing this. If you want to install it, you can use this this apt command, which is a Debian distribution tool for installing software. This gives us a view of all of the files and in our current directory and our subdirectory. The command that I use this in practice for is ls-r, capital R. For all of these commands, like ls, they take both arguments and flags or options. By convention, options are prefixed with a dash for single character options and a double dash for word options, multiple character options. So if I want to say -L, I want to view more information about the files in my current folder, -L will show us not only the name of the file, but it'll show the permissions, the user and group who owns it, the size, the date that it was modified, I think. And so the convention in these Unix commands is that you type the command, you type whatever options you want, whatever flags or options you want to that command, and then any arguments to that command. So here I'm saying I want to run the list command. I want to give it the -L option to list out all of the details about the file and the name of the folder or file that I want to list. So this is going to show me the list view, the long view for the new dir directory. If I want to combine commands, so say I want to do the recursive listing. So recursive listing will show each subdirectory's listings as well. I can combine these for single option commands. I can combine these without using extra hyphens. I can just glue together all of the single character flags or options that I want to use. So -L-R, capital R, will recursively go through each directory and subdirectory and show you the contents in long form of each of those directories. And I can even combine this with arguments and arguments to ls are other directories on my file system. For instance, if I want to look at the /etc directory, don't worry about what it is, then I can do a long listing recursively of this folder. And I've got tons and tons of folders here. They're all being listed out in long form. So that gets a little bit more advanced. One common one that I use all the time, I just sort of remember this by rote. Let me actually write this out. You don't necessarily have to use this. This just prints things with a human readable size. It shows everything in reverse order by date. So the older stuff is at the top and the newer stuff is at the bottom. So if I want to see files that are created more recently, I do this. I use this one all the time. I just remember this one and I just do it by muscle memory. But let me go over a couple more of these flags to ls. So -A will show you hidden files. So this is something like in a GUI. In a GUI, you have to go into some settings and say, well, view hidden files. Hidden files, I think, come from this view of the file system where a dot before the file name is considered a hidden file by convention. And the two hidden files that are always in your folder are dot, which refers to the current folder, and dot dot, which refers to the parent folder. And this is a hidden file that the Vagrant system software uses to maintain some state about to maintain some information about your virtual machine. Okay, so I know I'm going through some. This is a lot of stuff to digest. Don't worry about it too much. Review the notes, go over the command line guides that I'm going to give you later. Okay, so some people are already asking about move. In addition to copy, we have, so copy will make a copy of the file. So there'll be two instances of that file in your file system. Move will take a file. So like my sequence2 file, if I want to move it to another directory, I can use the mv command. And now sequence is gone. So it was here when I previously listed my folder, and now it's gone. Instead, if I list new dir, it's inside of new dir. Now move and rename are the same, because I can also take a file like long sequence and move it to, instead of a directory, I can move it to a different file or different file name. And so move, previously I had long sequence.txt, and now I've got a file named rename sequence.txt, and long sequence is gone. So moving and renaming are the same thing. They're just, it's a renaming for renaming. So somebody's asking, how do you move multiple directories into a new directory? Okay, so let's make multiple directories here. So moving multiple directories and files into is the same command. The move command takes a list of file names, and the very last file name, the very last name file is, the very last argument is the place, the destination that you want to move things to. So if I run this command, I'm going to move dir1, dir2, sequence, empty file, all to new dir. Now you have to be a little careful with this, because if you forget to put that last file, or you accidentally put a file name there, you may accidentally overwrite a file rather than moving something to a directory. So for instance, if I want to move new to new dir, I want to move it to new dir, dir1, but I accidentally typed dir. This is going to basically rename this file. It's going to move it into the new dir directory and give it another name, rather than moving it into the dir1 directory. Anyway, this is sort of a common gotcha. The main thing is use tab completion and make sure there's a slash at the end of what you're typing if you want to move something or copy something into a directory. So let's take a look at our new directory, and now you can see it has all the files that we have. Now copying directories is not going to work the way you might expect. So it's going to complain and say -r is not specified, because if you want to copy a directory, you have to use the recursive flag to copy to do it. So if I use the recursive flag, then it'll recursively go through the directories, copying each file one at a time. There's some like historical low and low level file system reasons for this. That take an OS course and you can see how these file systems are actually work at the low level, and it'll actually help reveal why these commands work the way they do. So just to kind of reiterate, these commands are operating at the are much more simple interfaces to your operating system. And so they're in a sense kind of reflecting what the kernel provides you. The lowest layer of the software of the operating system. It provides these library functionalities, and these utilities like copy and move are operating, some of these you could just sort of rewrite yourself. Some of them have very short source code, and you could rewrite them using the kernel system calls. And if you do that, take an OS course, that'll reveal to you why these commands work the way they do. But anyway, okay, we've gone quite a bit on these very basic commands. Let me move on to, so we've done directory hierarchy already. Okay, that's good. I think we've covered all of this. Yeah, one thing to point out is that the current directory / that's the current directory. I can just change directory all day long to the current directory. You can also use this for relative paths. So if I want to cat new file, it's the same thing with and without this /, essentially the same thing. There's some sort of specific reasons why you'd want to use /. One of the most important ones is running programs in your current directory. I'm sure you've all seen this in CS1. If you have a program in your current directory, you can't run it by just typing the program name. you have to type the / program name. Has everybody seen this? You guys have seen this, right? And I think the reasons for that is actually security reasons. You wouldn't want to accidentally run a similarly named program that exists in your current directory versus one that exists on your file system. You did it different in CS, okay. A.out, yeah, but it's the same idea. A.out is a program in your current directory, and you have to run it with /. You can't run it with .a.out. You have to run it with /a.out. Yeah, we won't go into it too much, but there's some environment variables. You have your path. So don't worry about this too much, but this path basically says where all the runnable programs are. So all of these programs like CP, if I type which, that tells me where that program lives. So they're actually not shell commands. Many of these are programs that someone has written. And when you type CP, it's actually just executing a program. And you can go view the source code of that and see how it works. Let's see, does anybody else have questions? We did exe. Okay, so we'll talk about I think the next thing is redirection. Yeah, okay. So in the Unix system world, and this I think has become standardized in the POSIX standard. Oh wait, somebody had a question about the difference between -r and -big R. For copy, I don't know the answer, so let's take a look at the copy instructions. Now I'm going to do a little trick. I'm going to use /to. So this is actually less. When I use the man page, it gives me the less utility. And you can search through that by doing / and then the thing you want to search. It's a little esoteric to use because of it actually uses regular expressions, which we'll talk about in this course. But anyway, I'm just going to search for -r. And it looks like in copy, they're the same thing. So -r, capital R, and -r are exactly the same thing. It's like using Control F. Exactly right. Yes, exactly right. So Control F is a GUI shortcut, common GUI shortcut for finding something. / is the same idea. / is a little bit more powerful because you can actually do pattern matching instructions. It's not just let me search for this exact word. It's let me search for this pattern. And we're going to go into that kind of pattern matching in this class and how they work from a operational point of view and also from a computational theory point of view. Regular expressions, if you haven't seen it before, are actually a really useful thing. Oh, that's a good question. So if somebody asked, how did I delete what I typed on the command line really quickly? By default, the bash prompt uses the Emacs editor's shortcuts. So I use this editing tool. This is my main driver programming editor. So some of the shortcuts here, you've got Control A to go to the beginning of a line. So just like, you can also use home or end. Control E for the, Control E for the end of the line. And Control K for kill line. So to delete it really quickly, just go back to the beginning of the line. So end of line, beginning of line. You can also use home and end. And Control K to kill. Control K to delete the whole line. And yes, as somebody said, up and down arrows. Oh, this is also essential for speed on the command line. Up and down arrows, or Control P for previous, Control N for next. Or up arrow, down arrow. Allows you to view all your previous commands. This is getting a little bit more advanced, but you can use, just like Control F, you can use Control R. This one, so don't worry about this if you're like not following along and this is getting too confusing. Don't worry about this. These are things that I use all the time. So if I want to go back to a previous command that I found, so I can't remember this long command that I that I Googled and I figured out this long command and I don't want to have to remember it again. Control R will do a reverse search. So this is a little tricky because you might be confused about how to get out of it. You can always use Control G to get out of reverse search. That's right. So somebody else pointed out history. You can use the history command. So just like any long text output, we can use the less command to allow us to navigate through this long list. So remember with less, you can use page up, page down. or control control F, control B. Don't worry about that too much. Page up, page down, and Q to get out. So remember, you're not going to have and be able to write any commands here. Use Q to get out. Okay, so that was a lot of stuff. Don't worry too much about that. Can you use Control R? Yeah, so Control R. So Control R brings up this new prompt that says I'm doing a reverse search. And if I just start typing in something, it'll automatically match how to pull a certain command from history. So this is Control R. Control R is one way to do it. So Control R, if I want to say, well, what was a command that I used that involved my sequence file? So I just typed in sequence here. So this is what I typed in, SEQ. And on the right is the command that it matched. If there's many commands that match, keep hitting Control R, and it'll sequence through all of the matching commands. You can see my cursor, my blinking cursor is highlighting each place where sequence matches. So I'm just cycling through all of my matched commands. Okay, this is a little bit more advanced, and then you can hit enter to just run that command right away. You got to be a little careful. Hit enter or some other command like home or end to bring that up. If you hit enter, it's just going to run the command. So that's a little bit of a kind of gotcha. You don't want to accidentally run some destructive command from Control R. Okay, so this is getting a little bit more fancy. This is a little less essential. The main takeaways here is like change directory and up and down to repeat commands, tab completion, ls. These are some of the most important things to remember. But yeah, this is why you can just be really, really fast on the command line. Get the history into a file. It's a good question. So history is just a program. And so we're talking about standard IO and standard output here. So let's go into standard IO here, and we can talk about that history command. Let me make sure I need to speed up a little bit here. We're almost at an hour, and so we should. Well, I guess we have an hour and 15. Okay, so history is just another command, another program. Now in the Unix standard, every program has standard input and output. There are three, so in the Unix, so take an operating system class to learn more about this, but in the Unix system, the file system is not just for storing programs and text, storing data on a disk. Files are the abstraction for doing input and output. Remember last week I ranted all about abstraction. And so the Unix designers, one of their main innovations was creating this file abstraction. And today we think of files as storage on a hard disk. But files are really a way to abstract away any kind of input and output. There's other ways to abstract this. So the Unix standard for doing network IO, for instance, is less popular. The Berkeley socket, the Berkeley distribution, the Berkeley Unix version, where they developed a lot of the internet technology, the protocols, their version of IO won out. And so when you do internet IO, networking IO, you're using the interface, the BSD socket interface. But the Unix interface for all IO is done through the file system. So there are special files that can actually say, my iPad, for displaying my iPad to the screen, there's actually a special file in the Unix file system that is reading in the data from the iPad screen capture. And I'm now writing it out to another program that is displaying it on the screen. But it's using a special file name in my file hierarchy. But anyway, so every program that runs, the operating system gives it three special files. And those files are the input and output files. Input, whatever the input and output to that program is. And so a program like ls, it also has three files created when it starts running, the input file and the two output files. ls doesn't take any input, as far as I understand, but its output by default, when we're running things on the command line, the output gets printed to the console, gets printed to the shell. So the reason that when I type ls, the reason that we see this being printed out to our screen is that ls is actually writing to a file, and that file happens to be our shell. If we use this greater than sign, the greater than sign redirects that output to another place of our choosing. For the greater than sign, this redirects to a file backed by our hard drive, a file in our file system. So if I do ls greater than sign lsout.txt, you can almost think of this as like a little arrow pointing to the file name that you want to write. So when I run this, I now have a new file called lsout, and I can use cat to view the contents of it. So there I ran cat without any arguments. Cat without any arguments by default reads from the standard input, which is reading from our console. So if I just start typing stuff here, it's going to be immediately printed out. It's going to be echoed to us. You can use Control-D or Control-C to end that. So I meant to type cat lsout, and that prints out the contents of lsout. So cat lsout. And as the student who was talking about history pointed out, so this is great. You guys are already putting things together. History is just a command that prints to standard output. By default, standard output, when we run it from the shell, prints to our console. So I can change where that standard output gets written to by using this greater than sign. So now I've got a file. So I'm going to start using this command that I regularly use because it shows me the most recent file written. Now I've got this new history file out. And I can use less on that. I can move it around. Here's the contents of new deer. I can move it around, and so on. So somebody didn't expect that to work? Yeah. So this is really the power of the command line, is that you can glue together many commands, many of these simple commands together. You can use them together to build up larger and larger, essentially, programs. And a lot of the things that would be really tedious to program are already given to you in a lot of small utilities that you can just glue together using these this standard IO to glue things together. So let me go over the standard IO real quick, and then I'll show how you can glue together multiple commands. So standard IO, there are three special files that every program is initialized with. There's the input, the output, and the error output. So this is just a convention that programs can write the output that the program behavior defines. So ls prints out the list of files, but the designer of the program can also write out error messages to a separate file. So by default, let me try to, yeah, okay. So I'm gonna do ls on new file and also a file that doesn't exist. This error message here is actually printed out to a different file. This is printed out to the standard error file. And new file.txt is printed out to the standard out file. When we're using the command line shell, the error file and the output file are the same. They're both being redirected to our console so that they're printed to us at the terminal. But I can explicitly redirect these separate files. I can explicitly redirect these separate files to be stored on my file system, to persistent files on my file system. So it's a little confusing because file is the name of all of these things, but there are special files that print to IO devices versus files that get written to disk. through the file system. So here I'm writing out the standard output file to standardout.txt, and I'm writing out the error file to standarderror.txt. So somebody mentioned this, what happens to these files? So they're non-persistent files. So when I say persistent, I'm not using very good language here. I'm not finding the right words for this. But basically, all files handle all I/O, handle all input and output. Some files are backed by the file system, which stores the hard disk file system, the file system that manages the directory hierarchy and files stored on persistent storage. And special files are mapped to input and output devices, peripherals. Some of those are real peripherals, like my screen capture card or a microphone. Some of those are kind of virtual peripherals, like our terminal window. So our terminal window is a special file that the bash shell writes out to, that under the hood writes out eventually to our, well, we're doing virtualization, but if you were on the bare metal, it would eventually write to your video card and write to your screen. So I'm not prepared to like use the correct language and talk about operating systems now. Take an OS class to learn about the details of this, but just be aware that files in Unix either mean files that are backed by your persistent storage in the file system, or they're special files that are backed by input-output devices, peripheral devices like the screen, microphones. Yeah, so sorry, persistent is a jargony term. Persistent storage versus like RAM storage, which is, you know, volatile memory. These are all the kind of technical jargon of the OS world. All right, so here I'm trying to list out two files. So I want to provide their long listing. I want to see all their information about them. And I want to print out the information for new file.txt and some non-existent file, which I think I misspelled. I can't remember how to spell. Linux is an implementation of the Unix. Basically, it was a clone of Unix. Unix was developed by AT&T. It was actually proprietary OS, and its interface was re-implemented by Linux and extended. All right, so I'm listing out these two things, and I want the standard output to go to standardout.txt, and I want the standard error to go to standardout.txt. Notice nothing shows up on the console. There's nothing here, because all that output is now being redirected to two persistent files backed by the hard drive. And I can use what to print these out if I want to view these files. A couple ways to do it. I can use cat. I can use less. So let's look at what the standard out looked like. And you see it's just printing out our new file.txt, the information about new file.txt. If I print out standard error, you'll see it's printing out this error message where that previously was just being printed out to the console. So this, we can see that there are actually two outputs that every program has. And this is by default. You may have, you've worked with this when you've programmed in C. When you use printf, running printf is equivalent to saying printf to standard out. But you could just as easily say printf to standard error or printf to some other file that you've opened previously. There's no distinction from the programming interface point of view between printing to the console and printing to the file. The calls, the library calls for doing that are identical. The reason that it gets printed out to your console is that the operating system sets you up, when you start the program, it sets you up with this standard out and standard error. This is similarly true for standard in. So fscanf, you say standard in, and that will, by default, when you run from the command line, it'll read from the console. But for a program like cat, which prints out a file that you give it, you can also change what its standard input is. So if I just run cat by itself, its standard input is from the command line. So anything I type here gets printed out to the command line. The code I was writing it in a comment. That was C code. I just wanted to write a comment. So if I want to write to a file, I can use cat to write. I showed this before. I can use cat to write to it, and by default, standard in will be reading from the command line shell. So here is the contents I want to write to the file. And so now my new file has this. But I can also redirect the standard input. So I can write to this new file again, but instead of having the standard input be set up to be my command line, my terminal, I can read from a different file, like, for instance, this long sequence file. This less than sign redirects the standard input. So now when I run it, no waiting for my input. The input has been redirected from this long sequence file. Oh, so somebody asked, how do you exit when you type cat? Sorry about that. So you type Control D. I didn't make that clear. Control D is a special character that means end of file. We'll go into that when we talk about characters. It is another way to copy a file, yeah, but it copies the file. It copies the file differently from. It's a way to copy the file. It's a way to copy the file. All right, so I know I'm going over through the stuff pretty quickly, but questions on this? I recommend just following along. It overwrites it, yeah. If you write to a file and redirect to it, it overwrites it. So the command line does not give you a lot of safety from blowing away files. Don't know what cat is. What does greater than versus less than do? So let me show this command here. So I don't think ls can actually take ls to file. Excuse me. Ls. So let me show this. Let me show this again. Maybe cat is not a great example to look at. Well, but anyway, so greater than redirects the output to a file. Less than redirects the input from a file. So think of it like an arrow. This arrow is pointing to my new file.txt, so it's going to write to that file. This less than sign points to the program, so it's going to read from that file. It's going to move that data to the program. So someone pointed out something which is a good point here. Double greater than sign will append to the file. That's a good point. So if I append to a file, so I've written hello to this file, and I can append to it. So Control D to escape. That's Control D to end input. Oh yeah, sorry. So it's you hold down Control and hit D. Yeah. So you can see now that I've used the double greater than sign in order to append to a file instead of blowing it away. That's a good point. All right, let me go through processes, redirecting processes real quick, and then let's take a break, and we'll continue after that break, because this is getting longer than I thought. We have a bunch of stuff to cover that you really need for the course to submit stuff. If you want to get out of a command, you can hold down Control and hit C. You can see it actually writes my character to the screen here. Be careful with Control D, because if you hit Control D on an empty command line, it logs you out. The shell treats end of file as ending the bash session. All right, the next thing I want to show is pipes. So we just saw how you can redirect the input and output of a program to files on your file system. But here's where the real power of the command line comes in. We can also redirect that input and output to other programs. So one really useful program that we need to kind of illustrate the utility of this is called grep. So grep will do string pattern matching in files. So if we look at our appended, look at our appended file here, grep will take a string and match, and only take out those lines from a file that match that string. And on this shell, it'll do color highlighting, which is kind of useful. So you can see my file has 2 lines in it, but if I use grep, it matches only those lines that match the string pattern here. And we'll see later how you can do wildcards and pattern matching. But for now, I'm just matching hello. And now with piping, I can glue together the input and output of multiple files, multiple programs. Here, I'm taking whatever the output of cat is, yeah, so some people are, I know this might be hard to follow along. I want to get through this stuff, but this is being recorded. Zoom is recording this. Let me actually I hope that Zoom is recording this. Yeah, Zoom is recording this. And you can go back and pause and follow along. It's just, I want to cover like a lot of material so that we can so you'll have like a crash course on this and you can go back and rewatch and see all the commands that I'm writing. But pipes are one of the most useful things in the Unix operating system. Because of this, every program has this standardized input and output. I can take the output of a program and instead of writing it to a file, I can redirect it or pipe it to the input of another program. The output of cat, which we've seen, well, I'm going to use a comment here. This hash mark is a comment, so I'm actually commenting this out. This is equivalent to just writing appended file. So this is what would normally happen. It would write to standard out, which is our console by default. But if I redirect it to grep, grep's input, now grep will take whatever the output of that cat command was and do its program. Its program is to filter or match any lines that match the string that I give it as the first argument. All right, so let me illustrate this with something a little more useful to try to drive this home. Then I'll review the processes and then let's take a break because it is getting late. All right, remember our ls command. We've got this long file listing. If I want to see just which commands, well, let's do this recursively actually. So I'm recursively going through all of my directories here. That output normally goes to the command line. If I redirect it to grep, grep will match only those lines that match this seq string. This pipe, this vertical bar pipe will take the output of whatever's before it and redirect it to the input of whatever's after it. So now I've got only those lines that matched my seq command. You guys with me on this? And what's really powerful about this is I can do an arbitrarily long sequence of these pipes. Oh yeah, so grep takes, I'll show this more. I'll talk about find in grep after the break, but I just want to kind of go over this piping. I can match only those things. Well, let's see if there's anything different. So I can use grep to match, to do multiple sets of these pipes. It operates like a filter. Grep operates like a filter. So, but basically the operating system just says you can redirect input and output to your heart's content. You can have any arbitrary sequence of programs where you redirect input and output. And by using the pre-made utilities like grep, you can build a filter. You can do search. You can do very sophisticated search. But there's no explicit functionality for doing this kind of filtering. For a GUI tool, they might design an interface. Here's how you filter. But with the Unix system, you can build your own filtering utility out of piping and some simple utilities that are given to you in a common distribution of Linux. So anyway, okay, so piping allows you to take the output of a program and redirect it to the input of a program. And to just pile on a little bit more, I can even use redirection to filter this. Yeah, we could do, so what are all the text files? What are all the files that match seq, match .txt, and then redirect this to a file. So pipe redirects input and output between running programs, and greater than or less than redirect them to and from files. So now I've got a file called filtered, which has the results of running ls, piping that output to grep, piping that output to grep again, to a different instance of grep, and then redirecting it to a file. So chew on that for a little bit, digest it, and let's take a break. If anyone wants to ask questions, I'll be here to wait during the break. Feel free to ask questions. So we'll reconvene in 10 minutes at around 11:30. Or let's do 10 minutes, 11:31. So sorry, this is going to be a little bit of a dense day today, but let's take a break. Reconvene at 11:31 in 10 minutes. So anyone who has questions, feel free. I'll be here to answer questions. Will you be tested on these? No, you're not going to be tested on them. This is just to make your programming life easier. We're going to do everything on the command line in this course, from compiling, running, testing, and submitting our code. And it'll be way, way easier if you have facility with the command line to do this. So somebody asked if there's any way to access directories or files we make in Vagrant from our OS. Yes. We covered this in last time, if you want to look at this in more detail in last class. But this folder, the reason I'm using this folder /vagrant is that if I go to, so if I exit my virtual machine, I've placed my Vagrant file and created my virtual machine in this folder, homepal, COP, blah, 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 blah. This folder by default is mapped to the /vagrant folder on my virtual machine. So this is my virtual machine folder here. And this is on my guest OS. This is my host OS's folder where I created my virtual machine. It gets mapped to this folder. So if you want to do editing in your own programmer editor that you're familiar with, then feel free to do that. And all changes that happen on your host OS in this folder will be reflected in your guest OS's folder. So somebody said, no command allows me to exit the cat file command. So the way to exit is to use hold down control and hit D. If any program is waiting for input, control D means end of input. So cat is by default reading from standard input and writing to standard, reading from the terminal as standard in and writing to the terminal as standard out. So if I'm stuck, it's just waiting for input. To end that file, to end that input, hold down control and hit D. Somebody hit enter a couple of times. Control D can only appear on a new line. Can we think of volatile RAM as faceless packets of bits behind the scenes? You can think of all data in any computing environment as faceless bits. Actually, that's the only mechanism that the computer has to store information and transmit information is through bits. You know, the low level is these are voltage signals. These are high and low voltage. I'm not an electrical engineer, but from what I understand, this is the way data is represented. And as we'll actually see in a bit after the break, all of these bits are faceless. They're given meaning by the programs we write to give them meaning. And we'll see that when we look at how text files work under the hood. So some student asked about Control D not letting them exit. So try hitting enter a couple times to make sure you're on a new line, and hit Control D when you're in cat. So it doesn't work. So hold down Control and hit C. That will kill the current program. So some programs can actually capture that and prevent you from using it. So Control C will send a signal to the program. So they're very different from the OS level. Control D will write an end of file character, I think that's what it is. Yeah, so Control D writes an end of file character, like a null character. And Control C uses the system to send a signal to your program to tell it that you want to exit. So Control Z is using the OS to, we're starting back up in 5 minutes at 11:31. Somebody mentioned a book called The Linux Command Line. That sounds good. I would recommend to do that. There was a lab last Friday. There is one today. The link is the same link as this class. Every single class, every week's lecture, every week's lab is through the exact same Zoom link. So if you're here, you just come to the same place. Best practice when you're done for the day to stop the VM. So I'm going to put this in a comment. Don't run this because it'll shut down your VM. But the kind of best practice way to do this is to use the shutdown command. You can certainly make Vagrant force it to halt, but it's kind of like using the hardware signal to power off your machine. I know OSs can capture this and shut down gracefully, but the nice sysadmin way to do this is to use the shutdown command. Why are we using a GNU Linux VM? We're using it because for a number of reasons. It's my preference. I use it in the environment. Standardize the environment. But also what's nice about it is it's free and open source. So from a student perspective, you're not tied to any proprietary software that you have to buy. So that's the free as in beer part. The free as in freedom part is that you also have access to all of the source code for this. And one consequence of that is you can actually look at the source code, you can tinker with it, you can modify it, you can learn how it works. That's not so easy to do with proprietary operating systems that are closed source. And perhaps even more importantly, from a practical point of view, is that the Unix operating system has one of the largest influences on the OS and computing world of any OS. And so even though GNU Linux is considered a separate operating system, Windows and Mac are POSIX compliant. So they implement the standard API that was developed pretty much by the Unix world. That's why it's called POSIX, I guess. I guess that's why it's called POSIX. Also, Mac under the hood is not using GNU Linux, but it is using a BSD, Berkeley Software Distribution based Linux, and also all of the same GNU tooling, more or less, so very similar tooling. So if you open up a terminal on a Mac OS, you're in a Unix terminal, and you have most of the commands that we have here, you have available to you in the Mac command line. Windows is a little different. They have their own shell, but from the syscall interface, I think they have some of the same system call interfaces that Unix has. And Windows also now has Windows subsystem for Linux, which is a built-in Linux system call interface. Oh yeah, good question. So somebody asked this last time as well. How do I have Notability paired with Zoom? I am using something that is less accessible to most people. I'm using a screen capture card, which are not cheap, because I really wanted to be able to do most of my work on my GNU Linux machine on my laptop, but also have a really nice drawing platform. So the iPad is excellent for drawing, also a very, very pricey option for that. And so I have a capture card hooked up to to my Linux machine, and there's a, whoops. So I've got a capture card hooked up, and I'm using this FFplay tools, FFmpeg. It's just a open source, free and open source video and audio encoding and decoding and playing. And you can see here, so this is getting a little off topic, but this /dev/video6. So in the Unix world, IO can be done through the file system, through our special files. So this /dev directory holds files where you can use the same reading and writing that we do with persistent files. You know, you can do piping and redirection. This FFplay utility just literally uses the same calls to open that file and read in the data, but instead of reading from hard disk bits, it's reading from the video capture card. So good question. What should be the big takeaways from this lecture? I would say the basic commands. So the big takeaways from this lecture are navigating the file system. So change directory, list directory, PWD for print working directory. Those are big takeaways. And tab completion. I would say if you don't remember anything from this, remember tab completion, that if you hit tab, it will automatically complete the name of the file for you. That is essential. Up and down arrows to repeat previous commands. Basically, you got to think lazy and impatient, you know, and the hubris to think that you can go and do everything from the command line, which you really can. You can do calendars, mail. The laziness to like not have to retype stuff out, and the impatience to try to do things really, really fast on the command line. So tab completion, hitting up and down arrows to repeat previous commands. Those are probably the biggest takeaways. Those are like some of the most useful parts. Okay, so that's how I do. Okay, yeah, I think I've covered all the questions. Did I miss any questions? Since Control-D and Control-D don't work exiting cat command, they should work. If you're still having trouble, hold down Control and hit Z. That will, so Control-Z is a signal, Control-C is a signal that's sent to the program to tell it, to ask it to stop. But it's just a request. The program can decide not to stop given that signal. Control-Z is a signal that at the OS level that will pause that program and return you to the command line shell. And that's something that the program cannot choose to ignore. Yeah, you can do everything on the command line. For a while I tried to do everything on the command line. I used a popular email utility called Mutt, which is a very, very nice utility. Why not always use Control-Z? Control-Z doesn't kill your program. Doesn't kill your process. So the most reliable is, I can actually show you the most reliable thing that you can do. So if I've got this running program, so cat, you should be able to end cat by holding Control-D or holding Control-C. So if you're in a program that won't respond to won't respond to end of input, won't respond to a request to kill, holding down Control and hitting Z is a signal that the kernel or the OS, the kernel will use to pause the program. So this is stuff you don't have to like remember. I'm dumping everything at you guys today on the command line. The jobs command will show you what programs are running but stopped. So these programs are still living in memory. They still have all their IO set up. Control-Z doesn't work either. So I have a suspicion that you are, let me see something here. So one little, try holding down Control and hitting Q. So try Control Q and see if, so there's like a mode in terminals that if you hit Control S accidentally, there's like some terminal settings. I actually don't remember what these do, but if you accidentally hit Control S, you'll go into this other mode in the kernel that you have to hit Control, or in the terminal that you have to hit Control Q to exit. All right, so if holding down Control Z doesn't work, then something else is wrong. Your OS does not receiving any signals at all. So we can talk in office hours if you have some specific system issue. Let's talk in office hours. To show you what to do about these stopped programs. So jobs will show you programs that are stopped or programs that are running in the background. There's office hours today at 1. If I really want to, so this actually leads to the next thing I want to show anyway, which is processes. So take an OS course to learn this stuff in more detail. But if I want to see what processes are currently running, I can type PS for processes. Take OS to learn more about this, but each running program on your machine is given a unique number, unique for that across all running programs. And this number, so here's my cat program. Control Shift C and Control Shift V will do cut and paste in a terminal depending on which system you're on. If I want to tell the program to, if I want to actually send the Control C signal, I can use kill. All right, so I'm just going to go through these commands. I'm not going to explain really what they do. I'm going to explain them from an operational point of view. Take OS or read up on these because I don't have time to go into this, and this is really not essential for this course. But basically, to put a running program in the background, hold down Control and hit Z. That will pause it. If I want it to continue running in the background, I hit BG for background. Now it says it's stopped, so it's running in the background now. If I want to kill it, then I can use kill and the name of the process. If it's really not responding to the kill command, this is like telling the system to tear down this process, and this is something that's that the program cannot choose to ignore. You use -9 for there's different signals that are by convention in the command line. If you have a program that's, so for instance, if I'm in less and I use Control Z to stop less, and I want to get back to that program, I can run it in the background with BG, but I can also bring it back to the foreground with FG. So now I'm running it back in foreground. All right, so that's like, this is not essential for the class. So let's talk to me in office hours if you want to learn more details about that, or review the lecture to look at that. Okay, so PS only shows the processes that are, I think, children of the current command line program. If you want to see everything across the whole system, do PS space AUX. There's many ways to do this. I just sort of memorize, muscle memory some of these. So that'll show you all the processes running across the whole system. So as before, we can use less to be able to have a nice navigable output here with page up and page down, Q to escape. We can also use grep to filter this stuff. So if I want to look at processes, lines that have Paul in it, or actually Paul is lines that have vagrant in it, then here's all the lines that match vagrant. So there's something run by root that has the word vagrant in it. To see the resource usage, you can type the command top. So all I did was type top here. Top is a little primitive, so there's a better tool called htop, which I've put in your provision files. So this is a more colorful, more useful version of top. It'll show you the CPU usage, memory usage. You can even kill, you can even kill stuff with F9 using this. We don't have a class Discord. Use Piazza for discussion in this course. All right, that's processes real quick. So take an OS course to learn more about this stuff. So some useful tools is man. We already talked about this. Find is a useful tool. So if I type find, it'll just list out recursively all the files and directories from my current folder. If I do find and another folder, like / is my root, the root of my file system tree, that'll just print out everything, every file name in the entire file system from that point you give it. This kind of pattern matching. So if I want to match anything that has the letter X in it, you can sort of see it's being highlighted here. The letter X is being highlighted here. So that's some useful stuff. grep we went over. Tar is useful, but let's leave that for another time. Tar is for doing zipping files, packing and unpacking files. Can also do compression. If you want to do editing on the command line, one of the most user-friendly one is called nano. It gives you the commands on the bottom. So it allows you to use the arrow keys, and it's a little more graphical-like. It's not graphical. If you want to exit, hit Control X, and you can use Y to save or no to not save. I'm a big fan of Emacs. Emacs is my main driver. Diff is really useful, allows you to compare files, but let's skip over some of this stuff. All right, OD is an actually useful one. We'll see this when we get into actually writing compilers. OD will show you the raw bytes in some byte representation of a file of interest. So if I type OD of from host, now remember, from host is a text file. So yeah, so raw host is a text file. Let's get one that has some more sensible text in it. Where do I put this stuff? All right, so I've got a file that has, it looks like a normal text file. If I use OD to this text file, I just get a bunch of random looking numbers. OD is a very old tool. It prints things out in octal representation. Octal is useful for maybe the old like PDP-11 or whatever that Unix was developed on. Hex is a little more common for programmers today. So -X will print out the raw bytes of this file in hex. Okay, so let me show you what the output of OD is. These numbers on the left, these are the position in the file. Oh, actually, let me use a different tool to make this a little clearer. Okay, it's the same thing. All right, there's better hex tools. All right, sorry. So this number here is the position in the file of those bytes. These 8 words here on the right are the raw bytes of the file. So to make this a little clearer what this format looks like, I'm going to use the -C argument. The -C argument prints out the raw bytes of this file, but using the C string representation. So this makes it a little clearer, right? So here at offset 0 in the file, I've got H, I've got E, L, L, O, /n. So remember in C, you do /n to create a new line. New line is just a single character. It has its own byte sequence. It's not, the space is just interpreted by your editor or your terminal to just move writing to the next line, visually the next line. But it's really just a single character in the file. So I've got 5 characters of, so lines, the notion of a line is not actually represented in the file. Lines, the notion of a visual line. The notion of a visual line is an interpretation of this character to draw the text in some way that we interpret as a separate line. But there's really no such thing as a line in the raw bytes of a file. The raw bytes of a file is just a sequence of binary numbers. It's the programs that we use that interpret these sequence of numbers to print out what we expect of a text file. So comparing these two representations of the same file, so this is the same file, appended file.txt. It's a little bit of an illusion to us to see it as hello, new line, more stuff. The only reason it looks like that is because there's a whole set of programs that reads, interprets, and prints out that file to look in that way, to look like that representation. But if we think about what somebody called the faceless bytes or the faceless bits behind the scenes, this representation here is a closer representation of what those raw bytes look like. It, of course, is still in text. It's still representing to us using a graphical drawing of the letter 6, but it's a representation that reflects what those raw bits are behind the scenes in hex. Does this make sense? Do you have questions about this? This is a little bit of a mind-warping part of computing, and for compilers, this is going to become an important thing to wrap our heads around. Makes sense. Okay, cool. So the reason H looks like H on the screen is not because there's anything behind, there's nothing physically on the machine that is storing an H. Or at least there's nothing in the file itself. There's nothing in the raw bytes that backs that appended file that is a representation of H. The representation of H happens because there's a convention called ASCII, a standard about which numbers represent which characters in the Latin alphabet. And so if we look at this table here, this table tells us in all the various numeric representations, decimal, hex, octal, HTML, which we don't need for those purposes, but it'll tell us which hex number should represent which character. But this is totally a man-made convention. I mean, this is all man-made stuff, but this is totally a convention. There's nothing physically built into the machine besides the programs that interpret these conventions that actually says anything about why hex 6.5 should be an H. The reason hex 6.5 is an H is purely a convention. If we look up here, if we look at hex 6.8, oh, whoops, this is Little Endian, so this is confusing me. Okay, so hex 6.8 here is an H. Hex 6.8 represents H, but it's not like there's any natural rule about computing that makes 6.8 represent an H. There's just humans that sat down and said, okay, look, we want all of our editors to work together. So we're all going to agree that if we have 6.8, which does have a physical representation in binary on a hard drive and on a processor, we're just going to say that if we have hex 6.8, all the tooling that is using text is just going to agree that if we see hex 6.8, we're going to use the character H. And so in a sense, there is a physical representation of H, but it's the program that processes that binary that is the representation of that H. And this is going to become really important when we talk about compilers, because in compilers, the whole game of compilers is taking what someone said, faceless bits, and interpreting that as a computation language and translating it to assembly. So somebody asked an interesting question here. How does the computer distinguish between the number 6.5 and A? So it depends on what you mean. This is where it becomes a little mind warping, because we have to distinguish between the representation of 6.5 versus the number 6.5 itself. So if we're thinking, this is getting back into like Plato's idealism, where you have a form and okay, I'm not good at philosophy, but there's the thing itself, the form, the object that's real, and then the representation of that object in the real world, like Plato's cave. And so in the math world, we think of the number 6.5 as existing independent of its representation. And so in some sense, we're doing the same thing here in information. Although instead of having some abstract non-physical thing, there's raw bytes. There's physical representations of voltage signals. And those are the representation, the physical representation of our math object of the number 65. But it becomes really confusing because usually when we have to have some representation when we're talking about the number 65. And when we say 65, we have a built-in assumption about a decimal representation. I think you all should have learned this in CS1, decimal versus hexadecimal representation. But where this comes into play in computing, particularly in system software and compilers, is that this 6.5 literally on the screen is not the binary representation. This is the ASCII representation being printed out through our I/O devices to the screen. Because there's some program that takes that binary representation and generates the hex representation of that on our screen. So, okay, good. It had some hex. So this becomes a little mind warpy. We'll get into this one next week when we actually build a compiler together, and we'll see some of why this becomes an issue. So somebody said, when you're coding in C, you can print char as an int, and it'll print the ASCII number. Yes, that's right. That's right. So this H here, the reason it's an H is because this OD program interpreted the raw bytes of the file, which had a 6.8 in it, and called whatever library functions it needed to in order to draw an H on the screen. So I just want to make this, so okay, so where this becomes very confusing, where's this file here? Oops. All right, here's my sequence of what look like numbers. But if I print out the hex representation of these numbers, so remember, this was a sequence from 1 to 100. I think I can actually do decimal here. I think this is decimal. Decimal, yeah, okay. So I can actually print out these numbers in decimal. And without going into detail, it's pretty clear that this is not printing out the numbers 1 to 100. This is printing out some other weird numbers. The reason for that is that even though the text is the number representations, these are actually the ASCII characters that represent number glyphs, the symbols for numbers, but not the numbers that the machine interprets as numbers. Numbers in the machine are binary numbers, the physical voltage signals, the processor that the processor works with. But when we're displaying the numbers, we're using the ASCII convention to represent those text versions of those numbers. So this is something that's very, very hard for me to explain. It'll become very clear when you do programming of the compiler. One way to bring this home is that in C, you have to use this A to I function, which I'm sure you've all seen A to I, right? What A to I is doing is it's saying that when you do standard in and you write input, you're writing ASCII characters. So if you write the number 1, so somebody asked, what does 2609 represent 1? So if you're writing ASCII numbers, the number 1 is hex 3.1 in ASCII code. So the number representation, so let me just do, I don't really use this decimal format very much. .26 is something else. What is 2.6? 2.6. I'm not really familiar with this the binary representation. Let's do hex. This is what I'm familiar with. I don't know how that decimal representation works, but you can see here that the decimal hex representation of 1 is 3.1, hex 3.1. That's the ASCII representation. That's the ASCII code for the character 1. And when I input that to a program, okay, so this is flipped, I think, because of endianness in Intel, I think. So 0A is new line. This is 0A. So this is hex 3.1 and new line character. It's flipped, I think, because of endianness. Okay, so when I input the number 1, I'm not actually inputting the number 1. I'm actually inputting the ASCII code that represents the number 1. And so this text file is not storing the bytes that represent 1 in the machine. And when you run A to I, we'll see it next week, but A to I is doing a very simple trick to convert this this ASCII code representation of the character of the number to the integer that's the machine representation of numbers. And we'll see a little trick that classic programmers use in classic code to convert between, that A to I can use to convert between ASCII and integers. Okay, questions on that? I know this is a little confusing. This will become a little clearer next week when we actually use this, when we actually have to deal with this when we program a compiler. Any questions on this? Okay, I think we're good so far. Where's my slides? All right, so this is going to be really, really essential for submitting your projects. Let's set up Git. I've created a little sandbox for Git that you could use to follow along with. You can feel free to accept this assignment. It's not graded or anything. It's just for practicing using Git. So this one I kind of want to go through a little more carefully, and I'll repeat this next week and in some of the project descriptions. Okay, if you've ever used Git before, you may have used Git clone and cloned this HTTP directory. What I want to show you today is how you can do a little bit more of a professional setup of your Git repository so that you can easily push and pull and synchronize with your repository version of Git. Let's see. So this is, all right, I'm just going to show you the commands. I'll just walk through it. The first thing we're going to do is we're going to follow these directions for creating a new repository. Okay. We're going to follow these commands for creating a repository. So let me set this up. In order to create a repository, we need some README. So I'm just going to copy these. I'm not going to go through too much about the details of these. So you can see they're using the echo command. So now we've got our, whoops, I need to create a new directory for my repository here. So here's my new directory. Let me create a folder or the file. Git init creates the repository. Git add adds a new file to the repository. If I say git status, I'll go into this a little more in a second, but this will show me all of the changes that are either pending or have been committed. So it says I've got a new file. I'm going to use git commit. And git commit is going to complain that I don't have an identity yet. So there's also instructions on the in the slides, but you can just copy and fill in these commands. So give it your email. Give it your name. Oh, this is a little annoying that it's wrapping. I don't want word wrapping. So I can actually see this here. Okay, so now I should be able to commit. So I do not recommend using -m. And I recommend that you give the name of the file that you're committing. Actually, I'll show a more tedious but more careful way to do committing. So it's going to bring you up in the nano editor by default. The idea behind Git is that each change you make to the software is tracked. And so you can track each little change to the software that you make through the entire history of the project. And in fact, the final or the current version of the code is really just the sum of all the changes to the code. And for reasons that hopefully will become clear later, the reason that we do this is that so that we can have a clear history of how the software changed. So if there were any problems or we need to go back and undo stuff, or we need to figure out how something was changed, we can go back in history and see the sequence of changes that led to the code. And this commit message is really important. This commit message describes the changes that happened. So it's very tempting to spend hours doing hundreds and hundreds of changes to your code and thousands of lines of changes, and then just make one big commit that says updated. That is the absolute worst kind of use of version control that you can have. And if you're working with anyone else, you're just going to make their life really hard. So remember last time I was talking all about making small incremental changes, breaking down the problem, and always making your implementation match the specification, but just having a limited specification. Using Git makes this really convenient to do. Someone asked about how do you install Git. If you've set up the Vagrant virtual machine, it will already be there for you. It's already set up with Git Vagrant automatically. So I really strongly recommend going back and getting Vagrant installed. Vagrant. Okay, so for the student who's having trouble, come to me in office hours, and we'll go through and make sure that you have Vagrant installed. If you have Vagrant and VirtualBox installed and using the Vagrant file that I gave you, and it was set up correctly, then you should have Git running. Okay, so to get out of this, use Control X to exit. Answer yes. It's going to ask you the file name to write to. Just hit Enter to accept that. And so I'm just running Git status to see what's happening. See the current state of my repository. It says everything's fine. There's nothing to commit. Working directory is clean. That means I have no current changes. If I want to see those changes, I type git log, and that'll show me the whole sequence of changes that I've made to this project. Okay, so to connect this to the remote repository, so I've made these changes locally on my machine. So I have this README file here. Git status tells me I'm on my master branch, which is I guess there might be some changes to what the standard is, but this is by convention the main version of your software, or the main development version. But on my GitHub repository, it's still telling me there's no files here, that I need to create a repository. In order to sync or push and pull in the Git lingo, remote repositories with local repositories, I can copy this git remote command here. This is going to tell my local repository that there is a remote version of this repository at this address. So I'm gonna go jump into my host OS for a second here, but I'll show you why later. Actually, let me show you where this goes wrong. So, because you'll encounter these problems as you do this yourself. And so the first thing it tells you so the next instruction is to push or sync my master branch with the origin repository. So when I added this remote repository, I called it origin, and I gave its address to be this git at GitHub, and this is GitHub's way of addressing their repositories. You can see your remote repositories by doing git remote -v, and this will show you that, okay, at origin this is the address of my origin. But still, my remote repository is not updated. In order to actually sync changes between two repositories, use the push command. The first time you run it, well, okay, so if I just say git push, it's going to complain that I have no upstream branch. So in order to make sure that the branch you have here is connected to the branch on your remote repository, you use this git set upstream. And what's useful about the command line is that I can use tab completion for command line flags as well for programs that support it. So this only has to be done once, and it just makes sure that the branch you have, the repository you have on your local machine is connected to the branch of the repository on your remote machine. It's going to ask you to verify the authenticity of GitHub. I'll show you in a second how to do this. For security purposes, you should never just say yes for this, because some man in the middle could be lying to you about this. This is a virtual machine, so I don't care so much on my machine. But you can actually go on the documentation of GitHub to confirm what their key fingerprint is. Take a security class, and they'll to learn more about this. But don't just accept these. Go actually verify that the owner of the server you're trying to connect to, this is their actual key fingerprint. So I'm going to assume that you've gone to GitHub's website and confirmed that this is the key. So now it's going to complain that I don't have access rights to this repository. Now, one thing you could do is you could use the HTTPS version URL to this, and it'll prompt you for username and password. But that's a massive pain, because you have to, every time you want to sync your repository, you have to type in your username and password. So I'm going to show you a little trick that you can do on the command line, and the instructions are actually here in my slides. They're here for how you can create an SSH key so that you can automatically log in with that key. So let me get to my slides so I don't have to remember these commands off the top of my head. And so the way you do this is we first are going to create a key. And just do this on your Vagrant machine so you don't blow away any existing keys you may have. So on your virtual machine, I'm going to create a key. It's going to ask me where to store it. I'm going to store it in the default location. It's a very good idea to give it a passphrase. It's definitely not recommended to not have a passphrase. You should definitely have a passphrase for this in good practice. Oh, it's actually complaining that my passphrase is too short. So I'm going to use a toy passphrase, which is not a secure one. Okay, and it's going to randomly generate a key for you using the entropy of your machine. All right, so now we've got our server key, or our SSH key. It's inside of this folder, the .ssh folder in your home folder. There are two files. IDRSA is your private key. This is the one you should never ever share with anyone or ever copy to anyone. Never ever share that file. The .pub one, that's the fingerprint of your key that you can tell GitHub, hey, this is the fingerprint of my key. If I can authenticate, if you see someone authenticate with this a key with this fingerprint, then let them in to access my account's repositories. So remember, to repeat, only share the .pub for public part of this key. Never, never, ever share the IDRSA part of this key. And always make sure you set a password, because that'll ensure that anyone who has access to your file system cannot then use this key and impersonate you. Okay, so now if I use this key, okay, so this is where I'm going to have to go to I won't be able to show you this because I haven't actually set up the key on GitHub. But what's going to happen is when you go to use this key, even though it saves your time from putting in the GitHub user ID and password, it's going to force you to write give the SSH key to you. So in order to avoid having to write the SSH key every time, I've installed a little utility. I've provisioned a little utility called Keychain. And so in order to keep your keys in memory, if you deleted those keys, you would no longer be able to authenticate using those keys anymore. But with GitHub, you can just go in and tell GitHub what those keys are. So there's directions here for doing that. I think I actually set up a screen here to show you how to do that. So in your account, you just go to settings. You won't be locked out as long as you have access to your GitHub account. You go to settings, SSH and GPG keys. I'm sorry, not GPG. You add a new SSH key and copy the .pub file there. Not the IDRSA file, the .pub file, only .pub file. That's the only thing that is safe-ish to share. I still wouldn't share it broadly, but you can share it with GitHub because that'll allow you to authenticate with GitHub using that key. So sorry, I'm going through this a little quickly, but it's being recorded, so you can go back and watch. So all right, so as soon as you set up that key and you tell GitHub what the public version of that key is, then in order to avoid having to type the password for the key in every time, use this keychain utility. So you start it up with eval and this magic sequence here. And then we're going to add that key. Here, we're adding the actual, the private key on our local machine. We're adding it to a special agent that will keep that key in memory so that whenever you need to use it, it'll just use the in-memory version. So it's a safer than having no password on your file, but it does keep your private key in memory. So if you're worried about an attacker has access to your memory, then that could be an issue. But it's much safer than having an unpassword protected key on your hard drive. So I'll add my key in here. Exactly. So somebody asked, can you create multiple keys for different computers or different users? Yes, exactly. So that's actually kind of practice I use. It's maybe slightly paranoid to use the same key, different keys for different machines. If somebody can ever take your public key and determine what your private key is, if that ever happens, maybe with quantum computing, maybe that'll happen with public keys. That could be an issue, although that could be an issue. Probably unlikely, but I'd like to kind of organize my keys to different machines. So now I've added that key to my in-memory SSH agent, who will now, this will now allow me to, here it won't because I haven't set up this user, but on my local machine, I have all this set up already. So I can do my push here on my host machine. And so see, it's now allowing me to track this local machine. So now I'm going to have to do everything on my local machine because this is what's set up. I have the keys set up already. Okay, so sorry to make that a little bit scattered. I'm maybe trying to rush a little bit too much, but I'm hoping you can just go back and see all the commands that I run and pause and everything. So now my repository has this README file in it. I've synced it with this README file. So let me step back a little bit and talk about Git a little bit more. As I said, Git is a version control software. So it allows you to take the changes from one copy of software and synchronize them with the changes for other copies of software. And it does this by having basically an append-only list of changes to your software. That append-only list is called the log. And each change, let me make some changes. So I'm going to edit this README file and say, these are changes So now I've edited this file. And you can see that when I say git status, it tells me a number of things. It says, okay, I'm up to date with master. Even though I've made changes locally, I'm up to date with master, the remote repository, because the log of commits is the same on both. but I have some changes that haven't been committed yet to my local repository. So on your local machine, there's almost like two versions of the repository, or at least there's two kind of copies going on. There's the set of commits, which is the actual software product. And then there's your working tree, which is the local changes that you have in your directory. So technically speaking, the copy of the repository is in this .git folder. So don't worry about that too much, but that's the kind of real Git repository. And in my current folder, that's where I have my working changes that may not have been committed to the actual repository yet. So you're not committing to a remote repository. You have a version of a copy of the repository that is just as real and just as authentic as any remote copy on your local machine. So this is why it's a decentralized version control system, because no particular copy technically is the official one. It's only official because some people agree that this is by convention, this is the agreed upon copy of the machine. So just because it's on GitHub doesn't mean it's the real copy of the repository. Anyone who clones that repository has in terms of the technology, has an equal standing repository. It just so happens that if everyone agrees that the GitHub version is the real version, then by convention, that is the real version. But it's just a convention. You have an equally real copy of that repository and all of its commits on your local machine. In this sandbox directory, I have the working copy of my source tree. And so any changes I make, these are, this git status tool will tell us anytime there's changes that have not been committed to the real version of the repository, the set of commits on the repository. Now I'm gonna say for at least while you're starting out using git commit, I'm gonna recommend that you use this git commit-p. This will walk you through every single change that you've made since last committing. It'll walk you through it and ask you if you want to stage that for committing to the real repository. So this is a little bit esoteric to use. You can use question mark to tell you what commands there are in this commit mode. But I can say no, I don't want to stage this for commit, or yes, I do want to stage this for commit. So I'm going to say yes. Yes, I want to commit this file. It's going to open up an editor. Once it's done going through all the changes, it's going to open up an editor and ask you to give a log message for this. So it's really important in version control to give detailed messages for these logs. It's really good for yourself, really good for other users. So I have added a message in the README. So you just save this file as I showed you before. And on the command line, this commit has finished. If I type git status, you'll see that it says the working tree is clean. There are no changes in my working directory that are different from what's committed in my real authentic version of the repository on my local machine. But it tells me a message here that my branch is ahead of the one on my remote repository. So even though on my local repository, this log shows all of the changes and there's nothing different in my working tree, git status shows me that there are some differences between the remote repository and the local repository. In order to move changes to and from remote repositories in my local repository, this is completely different from committing, remember. So committing was trying to synchronize my working tree with the log of changes on my local repository. Push and pull synchronize commits between remote and local repositories. So just to show you my remote repository, it just has one README file that says sandbox. When I say git push, oops, when I spell it correctly, when I say git push, it's going to synchronize any commits that I have on my local repository, not my working tree, but my local repository with the remote repository. And now you can see that changes that I made on the local repository are now reflected on the remote one. You can even see that we can do a git log remotely and see this log of messages on the remote machine. Questions on this so far for those who haven't worked with this is a very kind of a new concept and can be a little tricky to work through, particularly since it's decentralized. And it's easy to think, when we think centralization, we think, what's the real or the official one? But with decentralization, there is no center. Why don't I recommend commit-m? So let me show another way to commit. Let me show another way to commit here. So again, you make changes to a file, git status will tell you what's been modified. And you can use, so I don't recommend git commit because it encourages sort of, well, okay, this isn't my recommendation. This is others who use git. I used to use -m all the time. So git-m will allow you to write your message here. But I don't recommend doing that because it encourages kind of short, crappy commands, crappy log messages. Another reason I don't recommend it is if you don't put any files after it, Git will not, by default, Git will not just commit all your changes, because that's bad practice, just to commit all changes. It's very easy to lose track of what changes you're actually working on at the time and which ones you actually want to actually publish to the repository. So I don't recommend using -m because then you have to commit an entire file. If I do git -m and give it a file name, then it'll do the commit for me without bringing up that window. But if you use the, so let me edit this file again. If you use git commit, it brings up this editor to ask you to put in the changes. And the style of git commits is to have a short message here, a short high-level message here, and then any details about the commit. And so I use this frequently to make it really clear what changes I'm working on at this time. Yeah, so it also means that, so if you have commits that are spread across, if you have a commit that you want to commit that's spread across multiple files, then using git commit will walk you through each change. Now, if you know that all your changes are just in one file, then by all means use git commit and the file name. But I'd still recommend allowing the editor to come up so you can give yourself more space to write the command. And I'm not even going to show you the command for committing all changes. It's definitely bad practice. Yeah, so one thing in this class I want to try to get you used to is trying to be make nice bite-sized, clear, incremental changes to your code. And this dovetails really well with what I was talking about last time about implementation versus specification. If you can break down a change to your code that just adds a little augmentation to your specification, and you implement just that change, just that new part of your code, you implement just that change, and you've carefully carved out only those pieces you need to change to your code so that it's 100% working, passing all tests for that part of the specification, then you can clearly explain in your commit, okay, I've added this part, it's fully working, it builds, it tests, and it works. Even if you haven't finished the code yet, you can describe exactly what piece of the code you've gotten working. And ideally, if you're writing the code defensively, you've made sure that other test cases won't silently fail. So anyway, when we do the compiler next week together, which I hope I have time for, because this is taking, I'm spending way more time than I expected. I'll actually walk through doing these gits, using git live. For this class, you can just go through and just like walk through some of these commands and play with Git a little bit more. This is some kind of classic workflow. You can, yeah, anyway, we went through this already. Okay, that's not supposed to be there. All right, so that's Git. We'll go through this more next time when we program a compiler together. So next week, and I'll talk more in detail next week, but we're gonna program a compiler together, submit it via Git,
And that'll kind of take away the stress of doing the complex algorithms of a compiler, which are, not trivial. They're hard algorithms. And we're just gonna work together through all of the tooling to do coding on the command line using Git and GCC. All right, let's see if there are any questions here. How do you get the code from remote repo to local repo? Okay, that's a good question. You use git pull. Pull will take any changes, and there's a bunch of issues with what happens when these two repositories are out of sync or they have conflicting changes. There's a whole world of tools for doing that, which I won't show now. There's plenty of so at the end of these slides there are resources that you can read more about Git, but we'll go over like the common commands you'll need in this class next time. Yeah, as you can see, I have way too much stuff to go over, but we got 25 minutes. Okay, so there's a question about what IDE to use. You use any IDE you like, because you can edit your files on your host OS, and they'll be synchronized with the guest OS. You can still use command line Git to submit on your guest OS. And if you've got a app for Git that uses a GUI, you can definitely still use the command line. Yeah, I guess you can use the GUI. I mean, it'd be. I think at least for the first project, when you're not worried about like coding, I'd recommend working on the command line. It's useful because there are some things that GUIs won't allow you, don't make it easy to do for Git. There's some sort of detailed things. And it's also, I think, really useful. One thing that's useful about the command line is it gives you a much lower level view of what's happening in the software that you're using. All right, any other questions on Git? I know this was very fast. We'll practice using this next time more. All right, there are some people complaining about Mac and Catalina. Okay. All right. All right, let's move away from the command line a little bit. So for the rest of the class, I'm going to go over some basics of how your software actually becomes a runnable program on your machine. And then next time we'll talk about the coding tools. When we go into our toy compiler that we implement, I'll go over more tooling, and we'll actually work together on setting this up and running code and submitting stuff to Git. But for now, in order to understand compilers, we need to understand how a source file becomes a running process, an executable process on your system. So we got about 20 minutes left of lecture, and I think that should be just enough time to cover what I'd like to show you here. All right. So there are two major parts to how your software gets run on. Whoops, my iPad is running batteries. Let me charge this here. Okay. All right, there's two major parts. Your C file goes to your compiler, linker, and assembler, and it becomes an executable. So Unix doesn't use the .exe extension by convention, but we use that for our purposes. And your kernel or your operating system the loader part is what takes that executable program from disk and does all the setup it needs to start running from memory. And in the OS world, that's called a process. When you have machine code that's loaded into memory, and the processor jumps to the first instruction of that machine code, that's a running process. It's the operating system's way of managing all the running programs on your machine at the same time. We won't go into too much detail about how that works, but take an operating systems class. I'm teaching a graduate one next semester to see actually how that gets done in a kernel. So in detail, to go into a little bit more detail, there are several steps to taking the source code of your program and turning it into an executable file. So we've got the preprocessor, which is called CPP. This is not C++, but this is CPP. That produces a .i file, although it's in memory. That gets passed to your compiler, which is like GCC-C. That produces a .o file, which of course can also just happen in memory. That then gets passed to an assembler, or so GCC-C is the, let's actually include the assembler in here. So it gets passed to GCC-S, which produces an assembly file, which is a -s file. This gets sent to your assembler, which produces a .o file. This gets passed to the linker, which is confusingly called LD, which takes in a bunch of other library files or other object files to finally produce your executable. Make sense so far? So we've got C code. It gets preprocessed. Then it gets preprocessed. Then it gets compiled into assembly code. The assembly code gets assembled into machine code in an object file. And that object file gets linked with other object files to produce your executable file. So those are the steps of producing an executable file from machine code. So let's go through each step of this. Let me give myself some space here. All right, let me just create a simple C file here. All right, there's my hello world file. All right, the first thing that happens is the preprocessor is run. So you may not, I'm sure you've all used the preprocessor, but may not be familiar with the specifics of it. Oops. Okay, I've run the preprocessor, so let's take a look at what this preprocessed file looks like. And you might be a little surprised to see that it is huge. It is tons and tons and tons of stuff. So at the very bottom of this file is the source code that we thought we were writing. But what the preprocessor does, it does a number of things. That include directive at the top. This is actually not part of the C language. This is part of the preprocessor language. The preprocessor does three things. It basically cuts and pastes header files. So this header file is just a bunch of C code that's living in a well-defined place on your system, and it just basically pastes it into your file. So all that contents of this file that get printed out, that is everything from that standard .io.h file. It does conditional compilation. So if you've ever seen pound if-def before, it will allow you to conditionally include certain parts of your C code, and it also defines macros if you've ever seen pound define. But basically, it's like a kind of meta programmer. So it's a sort of mini programming language that runs at compile time that allows you to do some code generation and do modules, poor man's modules. Okay, so that's the first step. So now we've got this hello I file, which is a much larger C program than you probably expected from this tiny .c file. But we still have C program here. But now we have the C programming language. And the second step is to assemble the C file. I'm sorry, compile the C file. We run the compiler with gcc-S. And I'm going to turn off optimization. Don't worry about this. This just makes the code match the input C file a little bit more closely. So when I run that, I get a hello.s file. This S file contains assembly code in text format. So I think in CDA, which is a prerequisite, you've seen assembly. Don't worry too much about the details of this. We're going to go into Intel assembly later in this class, but you can see here, this is my printf function. We'll go over more details next week, but this is basically copying the address of the string here and calling the print function. This is the passing the argument to print. But okay, so there's our assembly. The next step is to assemble the file. So I'm going to take the assembly code and produce a .o file, which is an object file. And we can't really view this file in a text format because now we have a binary file. But we can see here, if we type the file program will tell you the type of the file. We'll try to figure out the type of file. You'll still hear there's all this, stuff here like ELF, 64-bit. This ELF is a object file format. It's an agreement between the compiler and the system tools and the operating system for how to store the machine code of a running program. So there's our object file. It just stores our machine code. We can actually use this useful tool called object dump to disassemble the file. So now we've recovered our assembly code from the machine code. We can also do some other things like show the binary of the program. Okay, once we have our object file, now in order to get it to be a runnable program, we need to link it with all of the libraries that we need to run it. So for instance, printing is found in some of the C standard libraries. The standard IO is part of the C standard library. And we need to link it with the C runtime that will allow the operating system to invoke our C program. So I'm going to run this not with the linker, which is called LD, because the amount of stuff for a modern operating system you need to link together is massive, and I'll show you that by using verbose output. So I'm going to create the hello.exe program from the hello.o object file. And you'll see here that this command here, this configured with command, these are basically parameters to the linker. So there's a ton of stuff that by default GCC links with your C program. Part of it is the standard libraries, and part of it is the C runtime, which I will talk about a little bit when we talk about how the program goes from an executable file into a running process. So the C runtime is, so the C runtime is one of the most important things we need in order to get our C program, which has a main method, how to get that to actually start running on your physical machine. And now we've got this hello.exe file, and it tells us it's also an ELF file. but it gives us other information about, it's what it's linked with and its executability. So there's a bunch of links here that for those who are really interested in the low-level details about this can take a look at for what's going on here with these dynamic linking and loading. Okay, so in summary, our C file gets pre-processed, and that does some meta programming, some compile time programming to cut and paste code to make our final C file. Our C file gets turned into assembly file. That assembly file gets assembled into object code in the ELF file format on our machine, in some standard conventional format that all the binary tools use. And then the linker combines that with any libraries and any loader conventions like the C runtime into an executable file. That's turning a source file into an executable file. And if we look at, say, the bytes of our source file, notice that this is ASCII code. These are ASCII codes. If we look at the hex, you'll note, if you were to look into the detail at this, these are ASCII symbols of the code. There is no machine that I know of that actually interprets ASCII in the processor and runs a C program. What gets run is the ASCII code of the binary code of our executable. Whoops, not OD, object dump. So this is the disassembled version of our executable code. This represents much closer the actual binary that gets run by the processor, something that's very, very different from the C code. And notice that the C code, even if it has numbers in it, those numbers are just characters in ASCII. Those are not actually numbers that the machine recognizes or the machine processes. So let's see if there were some questions here. Your slides make you feel like a hacker. Yeah, I like the black on white background. Also, I'm using a JavaScript-based, an Emacs and JavaScript-based set of utilities for making slides. Do a lot of your students end up completing a full compiler? Yes, most do. The compiler in this class is going to be a little bit more involved, but you're going to have more of the compiler given to you. So yes, most students do end up completing a full compiler because we're doing a compiler for a much smaller language. All right, other questions from an executable, from a C file to an executable? The next piece to this puzzle is how a executable file becomes a running process, how it actually gets, how it actually starts running on your physical hardware. Oops. Oh, okay, I have a diagram for this already. So I'm not going to go into too much detail about this because this is more of an OS class thing. But basically you have this divide between user space and kernel space. The kernel space is basically a library, a set of library calls that allow you to do things like open files, read and write to graphics cards, perhaps. And it also has an interface for executing programs. The kernel is the lowest layer of software. It mediates all hardware access. So without any special system calls, the user space applications like your C programs cannot have any direct access to the hardware. No intentional access. So security compromises can allow you to get access to hardware. But the intention is that user level programs do not have direct access to hardware. The kernel provides us a library of system calls or syscalls to your application. So printf behind the scenes is calling open and write, or calling write, which is a syscall. And the kernel manages resources. So it shares the processor among different running programs called processes, and it shares memory among different running programs using virtual memory. take an operating system class to learn more about how these work. But for our purposes, the main issue is how does a running program, since it can't actually tell the processor, hey, start running me, and it can't tell the RAM, hey, load my machine code in memory. It can't do any of that from user space. So it asks the kernel to say, hey, here's some machine code, please run this for me. And so in order to do this, we need some agreed on format for our binary code. And this is that ELF format. And there are other formats. Windows has their own format. Mac, there are other Unix-based ones. But by having this format, the system tools, the compiler, and the kernel can agree on what the machine code format will be, because remember, it's all just raw bytes. So some of it is telling you, some of it may be data, some of it might be code. And so the ELF format tells the kernel, here's where the machine code is, here's what you need to load in memory for me, and then start running. Now, this loader also provides a convention about where the first instruction you should branch to in order to start running that machine code. And by convention, this is labeled _start. You can change this, but the convention is _start. Now, if you've ever been wondering, why is it that you write a function called main to run your program when you're doing assembly, you just start running code from the beginning of it, is that actually main is not the first thing that gets run when you execute your program. The first thing that gets run by convention is this start label. It's not even a function there are no functions at the assembly level, but this start label, or this start function, for lack of a better word, is where your program begins execution. And it's the C runtime, which is a special library that actually implements start for you. It implements machine code there. And it's that start function, or that start code, that C runtime code, that actually calls your main function after it does some setup of memory. So the system call that creates the running process is called exec. It's a family of system calls that's part of the POSIX standard. GNU Linux has it. It brings the binary file in memory, goes to that start location, and lets it run. And this syscall is where those argc and argv arguments come from. Just by convention, the kernel itself is aware of parameters to programs. And so the kernel itself in the syscall, it supports taking those in and it passes them along to the process. It puts them in memory for the process. And part of what the C runtime does is it takes them and passes them as parameters to your main function. Loader does a bunch of other stuff. It sets up the IO, it sets up standard IO. And so you can actually see this using the exec, bash command. So as I said, the C runtime defines this entry point, start. So it sets up a bunch of stuff. It sets up signaling, standard IO, sets up arguments. And actually when main is done, this is why you don't have to call exit yourself. When main is done, you just return. It's the C runtime that actually calls exit and stops the process. Exit is another system call that stops the process. And it also takes this return value and passes it to the exit system call, because also by convention, every program that finishes has an exit code so that the programmer can communicate to the user of that code whether the program successfully ran or had some sort of error. And so there's a really useful link here on an operating system development site. Oh, interesting. Okay, well, you can view that at a later time. Okay, so in summary, the C file gets turned into an executable by the compiler, the assembler, and the linker. And the loader is what works with at the kernel level to take that machine code in an agreed on format and put it into memory and start it running. So there's some really good links that go in great detail about how this process works, specifically in the Linux kernel. So I recommend reading those if you have interest in this. Take an operating system class if you want to learn how this stuff actually works. The kernel is actually, to me, the kernel and the compiler are just the two core parts, or at least the system software. They're the two core parts of any computing device. They're the lowest layer of software on pretty much every computing device. they're what allow computing devices to run and allow you to make programs that can work, can use and harness these computing devices. Okay, I think that is a nice clean break from the rest. We will cover using GCC and Make next time. So just to kind of wrap up today, we did a sort of extensive and scattered view of the command line. The main takeaway is use tab completion, use the up and down arrows to repeat commands, use change directory, ls, pwd to know where you are and know what files there are. We looked at Git. So we'll get some more practical experience with this, but I'd recommend using that sandbox just to play around setting this up, getting your SSH keys set up. There are good articles here that you can follow to help set this up. And we looked at how a text file, which the machine has no ability to run, how it actually gets turned into a running process. So look at these resources. This War Games is very popular among students. It's a good way to get kind of fun practice using the command line. It makes you log into a bunch of servers and do increasingly difficult command line tasks to find the next server. There's also really good tutorials on, there's tons of tutorials on Bash. I'm by no means giving a comprehensive explanation of the command line. We'll go over C and Make files next time. And here's some guides on using Git. I recommend going through these as well to kind of understand the philosophy behind Git and all that. Okay, questions. So the lecture is officially over now. I'll take questions now for the next couple of minutes, and then I'll be in the gather.town room for office hours. So thanks everybody. Have a good day. I hope that was okay. I hope that wasn't too scattered. I know it was a little sort of a lot to cover, but for the command line, just go back and watch, pause, and look at the command that I wrote.
Is there going to be a lot?
Stick around here for a couple minutes for questions, and then I'll just move over to Gather. Oh, lab will just, for any of those who are still having issue with getting Vagrant set up, you can ask Josh about that. If you want to go through any of the command line stuff or setting up Git. I'm not taking attendance strictly in this class, and everything is recorded, so you can always go back and watch the lecture. For some it's easier to watch live. So if you don't have issues with Vagrant and everything today was clear, then that's what lab is going to be covering. So if you don't feel you need to go, that's okay, but they're also being recorded if you need to go back and look at them. So somebody asked, what is lab covering for each? So for each semester, I expect that lab will just cover what we did in basically the last 2 lectures. So it'll help reiterate those who are still catching up with the previous week's lecture, and it'll help answer any questions in that day's lecture. Okay. There's no further questions. Yeah, thank you all. Have a good long weekend as well, everybody. And otherwise, those who would like to come to office hours, I'll go to Gather. I'll be there at 1. I'm going to take a little break, and I'll be there at 1. Have a good one, everyone. Take care.